Hi, Kurt. How are you?
Pretty good. Just trying to figure out how the controls work on a phone here. Okay.
Did you get the slides in the email?
I'd have to go check, but it's a little hard when my phone's spooled up displaying this video.
Okay.
Yes, I've got the slides here.
Okay. Very good. Very good. Let's wait a couple of minutes if anyone will desire to join, and we can either chat or go over the material using this opportunity.
Sounds good. Hopefully someone else will try to log on.
Oh, David, I see you are in this list of connected people. Yeah, we are waiting for a couple of minutes if anyone else will join. By now we have 3 participants: Kurt, David, and myself. So probably no one is going to pop up in additions. We could start, and maybe I will need to repeat this material anyway for majority, but you guys will have chance to cover it deeper. So, and feel free to like put your microphones on, stop me, and just convert it into discussion on like less formal subjects. Also, Anas is also was connected and then disconnected. So please, if you want to stop me, use microphone and voice, because when I will put the presentation on, it will block me from seeing who else is on the connection. So we are going to get this slide as the last one in this meeting, and there is a chance that we need to repeat this material again when everyone will join. But you guys may benefit. And I'm not doing recording myself, but hopefully there is a bridge recording by the conference rooms. So if you feel comfortable with this slide, then you basically do not need the rest. Who needs the subject that we are trying to cover? Generally, those who are dealing with radicals and magnetic materials. Personally, based on your projects, David may benefit of it. Kurt may benefit of it. But mostly, from what I know about the project that you have chosen, it is likely Ben Jeffrey, because his project includes metal organic complex that may take different oxidation states, and separate treating of spin up and spin down is needed. Yes?
Ты что, ты что, с работы, что ли, собрался?
No, it is a lecture. There are students online.
О, то есть ты будешь опять что-то согрела?
It's not long. It's like 40 minutes. So it is a little bit of additional background to the material that was presented by Queenie and Mead on our session. So what do we do? What do we do for the treating systems with unpaired spin? So the stuff that is shown in red handwriting is the regular expressions for local density approximation. The typed expression in the red frame is how the local density approximation is modified when we are going to spin polarized case with spin alpha and spin beta. So why I'm talking about LDA and LSDA only? Because it is simple. It is definitely most pathetic functional, and it is least useful for practical applications. But we do need it because one can write all equations in one slide, and it is easier to prove this. But a lot of principles are ported, funneled, copied into other functionals as well. So the red things just wrap around some notations. So the density functional local density approximation tells the total energy as functional of density is integral of the density to the power 4 over 3. Very similar to Thomas Fermi. Thomas Fermi is 5 over 3. LDA is 4 over 3. We can decompose it as a product as rho in the power 1 or 3/3 times rho in the power 1/3. And then this rho in the power 1 can be combined with dr, with integration over space, as increment of density. So now we are looking on the top equation, rightmost thing. So integral of the rho to the power 1/3 over increment of density will give us total energy. Now, if we apply functional derivative to the first line, which means increment of energy divided by increment of density. So if we apply functional derivative, we'll get that functional derivative of total energy in respect to change of the density will be density in the power 1/3. So this, I would write it is equal the potential that enters the Chem procedure. And after this semicolon, it's just returning back to the first line. So if we integrate the derivative, we are getting our function back, or functional. So here the only thing that we, instead of integration and differentiation, we have functional derivative and functional integration. So functional integration of functional derivative restores the functional. Now, what is in the last line which is typed? So it is functional of density in case we do have spin up and spin down. It will be total density and then components of the same power 4/3 for alpha and beta. But they are expressed in terms of this strange letter. I do not know how to pronounce it. Xi. And this is a notation that is used inside the VASP software. So if you are going to, again, why should you waste time on these things? For practical work, you do have all components. So this little theoretical background is needed in case you will be left alone in front of aggressive evaluators of your work, and they will start giving you a hard time about the theoretical background. So you need to just provide a little bit of what is inside the code. And when we go behind singlet, when we go into spins that can have alpha and beta projections, there are little adjustments to this functional theory. From practical thing, you have DOS for spin up and spin down, what Enos was showing in his last slide, and there are some traces of this in the spectra. And in the theoretical part, there are contributions from spin up and spin down density into total energy. So if you get comfortable with this equation by the end of the meeting, the goal will be completed. So here, those are our two theorems that from density determines everything, including external potential, and the absolutely correct density will provide you absolute minimum of energy. And here is the Chem procedure that on Tuesday was described by Nathan. So look here in this box, there is an index theta underneath of index I underneath of theta. Okay. So spin and magnetism are connected. So for magnetic materials, one needs open shell models. If we are looking back on the background of quantum theory, then spin is I need to ensure and look if anyone is still here and if anyone is interested in what I'm talking. Please give. I see only David, so give me some. Please give me some signs. Is it like okay off subject, or should I stop or slow down? Some feedback.
Going fine for me.
Okay, very good, very good.
It's going fine for me as well.
Okay, thank you for. So this the only important thing is the slide that I discussed in details. The rest will be just where it comes from. So here are spin operators. If we are writing down quantum equations only for spin degree of freedom, allowing it like flipping up and down, and we have only spin 1/2, then Hamiltonian, everything, energy, everything that relates to our small world, where there are only two quantum states, spin up and spin down. If we remove everything else from the universe, so universe is only one electron that can take states up and down, nothing else. And if you want to build quantum mechanics for it, then it will have the operators that I quickly go over. But if you never saw them before, you may discuss it in private again. So there are spin raising S+ and spin lowering operators. So if our system was in spin up, then lowering operator will make it down. If our spin was down, raising operator will make it up. And by adding together or subtracting this spin operators, one is getting to projections of spin onto x and y directions in space. So although spin has only two quantum states, there is a connection between spin and projections in three-dimensional space. So by combining some basic spin operators, and there is a third one, SZ, which is a little more complicated, plus times minus minus S minus times S plus, one can obtain things that will be corresponding to magnetization of a material that includes the spin on experiment. If the spin comes not from, if the spin comes from electron, it will correspond to EPR, electronic paramagnetic resonance. If the spin originates from nuclear spin, then it will be NMR experiment, which measures, it includes some things that measures magnetization X, Y, and Z, or quickly changing magnetization because it is a radio frequency changing field. Make sense? More or less? Like magnetic field has three projections, and anything with spin will also create, will contribute to magnetic field in three projections. Okay. So wave function, if there is a spin, we need probability that it is up, we need the probability that it is down. But if we are restoring, we are coming back to the universe where electron not only changes spin but also can travel, then we will have probability in space. So this upper component, phi sub alpha, is probability that electron will spin up, locates somewhere in space as function of r. Wave function phi sub beta is that spin with projection down is located somewhere in space r. And we need to track these two components all the time simultaneously for alpha and beta, because their absolute value square together will give 1. So you have one electron, it has probability to be up or down, and it can be at some position of space. So we are forwarding, projecting, improving, expanding density functional theory to this situation when electron is not just takes position in space, but also has projections up or down. Okay. if our wave function is formulated in terms of this spin components, then multiplying row by column, we will get such a scalar product which should give us normalization. So normalization looks a little more sophisticated in the spin thing. If we multiply column by row, instead of scalar, instead of number, it will give a matrix. And this matrix, which will be, do you see my mouse? Please give me a sign. You do not see? Okay.
I do not see the
No.
mouse. I just see the screen.
Okay. Let me check how can I do it. Do you see me moving the object up and down? Or not quite?
Yes, I can see the object moving up and down.
Oh, okay, good. Then I have an idea how to focus. Do you have an arrow? Do you see my arrow?
Yes, I can see the arrow.
Okay, so if we multiply the spinner, so this combination of wave functions for up and down, two-component vector is called spinner. If we multiply spinner as column times spinner as row, we are getting matrix. And we know that if we multiply, if we create it is distribution in space and it is density. And when we in this 2x2 matrix with 4 elements, the first one, phi alpha times phi star alpha is density. Probability is that spin with projection alpha does exist. Along the diagonal, this one is that spin with projection beta does exist, density, probability. And for basic primitive calculations, we need only these two projections. If there will be sophisticated magnetic phenomena, we would use only also off-diagonal elements. Okay, a little of traditional physical chemistry or basic physics. So what is energy of spin in magnetic field? Or let me formulate in a more positive way. If you have spin and you have magnetic field, it is same like electric dipole in electric field. The energy will be non-zero. The compass in magnetic field will try to rotate along the magnetic field. Because if it will rotate against, energy will increase. So there is the same situation with electron. So if we multiply this S vector, which is composed of this Sx, Sy, Sz projections times vector of magnetic field, we will get some energy. And just opening the scalar product, the energy of spin in magnetic field is products of X projection of spin times X projection of field, and so forth. In most applications, it is completely legitimate to forget about the X and Y components, because we can always choose direction. In our laboratory, we can align magnetic field along Z projection, and then Hamiltonian will look simpler. So this is like, do not focus too much, do not spend your intellectual effort. Those are just fluffy background. I will tell when it will be important things. So arrow. Okay. We in our laboratory system we can tell that x and y projections of spin are zero, and there is only z. And then energy of our system with unpaired spin in magnetic field is just as z projection. I better skip it. And if we, I'm going to focus and maybe frame equation. So I'm going to speak only about the frame equation so that we do not bother each other too much. By applying standard protocols for quantum mechanics of spin, this energy of spin and magnetic field can be expressed as subtraction of density with spin up and density minus spin down. So a little logic behind it. If number of spins up and number of spin down is equal, if you have singlet system, then there will be no interaction with magnetic field. Does it sound reasonable? Yes or no? So, but if spins are unpaired, there will be additional component to energy because they are amount of spins up and spin down is not equal. Just this subtraction. Therefore, systems with unpaired spins will be magnetic. Okay? So, how do we process these unpaired spins in VASP? What does it mean? So, we compose spin up projection as adding together probability density of all occupied orbitals with spin alpha. So we just look for the list of Queenie was showing that there are two lists of orbitals for spin component 1, spin component 2, spin alpha, spin beta. And for each of them, we are adding together. So we are adding together partial charge densities, orbital squared, up to highest occupied for spin alpha, right? And then we go across all orbitals with spin down. So we add together density of all orbitals with spin beta. And it is interesting that if it is a spin polarized system with unequal number of spins up and spin down, it will be different numbers. So we add together different number of orbitals, different densities. Queenie has connected. Hello, Queenie. Even if you do not speak back, I'm happy to see your name among connected ones. And we are discussing your material of spin polarized density. So those 1 alpha, 1, 2 alpha is your first list of orbitals with occupations 1. And the next line is second list of orbitals with occupation 1. As soon as they become unoccupied, we stop adding them together. And this develops as two densities. One density for all electrons, total density for all electrons with spin up, spin alpha, and here density of all electrons with spin beta. And in case we are dealing with magnetic materials, this HOMO, highest occupied with spin alpha, is not equal with highest occupied with spin beta. If If they are equal, then we are not in spin, we do not need any treatment of spin. Okay, so here is a little hocus pocus, a little wrapping around with equations. So if you do have density with for spin alpha and spin beta, and they are not yet integrated, they are distributed in space. But you can integrate them. So if you integrate rho sub alpha, you are getting, if you, let me show it with arrow. If you integrate rho sub alpha, you are getting n sub alpha, number of electrons spin up. If you're integrating rho sub beta, you are getting number of electrons spin down. If you're integrating summation of these two things, you get total number of electrons up plus number of electrons down, which will be total number of electrons, right? If in your system, part of electrons have spin up, part of electrons have spin down. If it would be a singlet, this number will be equal, and you just multiply 1 by 2 and or occupy each orbital with 2 spins, and then you get total number of electrons. If you treat them separately, you need to find n alpha and n beta, add them together, and you get total number of electrons. In addition, you can do another very simple experiment. You can integrate alpha and beta, or you can integrate subtraction of alpha and beta. And then it will be number of electrons up minus number of electrons down. If this number equals 0, then we do not need spin at all. But if this number differs from 0, if it is 1, 2, 3, then we really need this spin polarization. And it is actually, we call it spin polarization, because like spin alpha and spin beta are not equal. N alpha minus n beta delta n, spin polarization. By the way, if you are proficient in inorganic chemistry, this spin polarization parameter can be connected to very canonical observables in basic inorganic chemistry. So since each electron has spin 1/2, then if you divide number of unpaired spins, number of unpaired spins. If you multiply the number of unpaired spins by 1/2, you will get overall spin of the system. So we are going towards like high spin and low spin stuff. Multiply by 1/2. And if you take the spin, multiply by 2 and add 1, you will get multiplicity. Also standard thing in the inorganic chemistry. So if we are getting spin, spin equals 0, 1/2, 2/2, which is 1, 3/2, then the multiplicity will be 1, 2, 3, 4, and they will be referred to by words singlet, doublet, triplet, quartet, right? So there is a connection. This computational chemistry is not very far from inorganic chemistry. It's all for same things. Okay. Now a little bit more of tricks, but I hope very much that you can how to say, tolerate them. It's not super complicated. So what if we design a new parameter? If you design a new parameter, a new variable, which will be density of spin alpha minus density of spin beta, divided by density of spin alpha plus density of spin beta. It is the same as spin polarization, but it is space site specific. It's not overall parameter, but it depends on position. So this parameter is referred to as spin density. And if you are looking inside per charge, it is what you see in the second fragment. If you do per charge for spin, remember lab number 11, and the stuff that looks like a hex nut around vanadium ion. So it looks like an orbital, but it was like 8 petals, because it is 4 petals for 1D orbital minus 4 petals for another one, and then it looks something more fluffy, but it is distributed in space. So actually the spin density is the thing that is being used inside density functional theory. It's not the best observable for us humans, but it is really comfortable to derive equations. And this spin density is connected to our to the things that we like as humans. So if we take this spin density and just add +1, then we do this rho alpha minus rho beta divided by rho alpha plus rho beta plus, and then we have the same in the numerator and denominator, alpha plus beta, alpha plus beta. We have the common denominator, and in the numerator beta subtracts, and we have only alpha, right? So if you put 1/2 on up front and multiply it by density, so spin polarization +1 multiplied by total density times 1/2 will give you density of spin alpha. So when you're using VMD to plot spin orbitals, it is you have the options to spin to show total spin density or alpha projection or beta projection. So it is the operation that VMD is doing for you while processing VASP output per charge file. Same thing. If we subtract spin density -1, so rho alpha minus rho beta divided by the sum, subtract alpha plus beta at the numerator, alpha plus beta in the denominator, we are deleting alpha and staying only with beta. So we better flip the signs. 1 minus spin density multiplied by total density multiplied 1/2 will give you density of beta electrons. Yeah, it's just typed nicely. So spin density, alpha minus beta divided by alpha plus beta. And here is the way how you extract spin density. Okay, so now with this new, we didn't get anything in principle new. It's just new notation that we need to adopt when we go from singlets to like doublets, triplets, quadruplets. So just 2 densities instead of 1. Now, if we go from LDA to spin situation, then we need to place the letter S from LDA to SLDA. So we add the spin. So in regular LDA functional, density is 4/3 in power 4/3 integrated, or density in power 1/3 functional integral over density will give you total energy. In case we are dealing with a spin polarized situation, our total energy depends on each of the spin components in the same way as on the as before. So it is spin alpha to the power 4/3, spin beta power 4/3 integrate. But for the sake of simplicity of equations, not for us, not in this class, but if one is going further to more complicated functionals, it is so much more convenient to use spin polarization instead of spin alpha and spin beta. It was double checked by generations of scientists, and we just need to adopt the notation. So this LSDA is a function built in the same way as we did for singlet LDA. But now we want to reformulate. Instead of functional of alpha and beta density, we are going to formulate it as functional of total density and spin density. So instead of rho alpha, we are plugging in a little protocol how we convert spin, how we obtain spin alpha density out of total density and spin polarization and spin density, right? And then we put everything into the power 4/3. Then we do the same trick for the beta density, for this one. So we plug in expression for rho sub beta in terms of total density and spin density. And then we put this power 4/3 on the top of it. Now we can observe that the total density into the power 4/3 can be taken outside of a bracket, right? And inside of a bracket, we do have only spin density plus or minus 1 in the power 4/3. So this is equation that we were discussing at the beginning of the meeting. This is like standard way to process. It is how it is in practice done, how the equations are written down in the codes for DFT. So one takes total density and spin density and processes it towards the total energy. In case we go beyond LDA, equations become more complicated, but they keep this term as like first term or zeroth term in expansion. They add some additional correction terms. So this slide doesn't show anything new. It is just typed in what we discussed. So density alpha, density beta, and then we convert it into total density and spin density into the appropriate powers. So this is an equation that we may want to be not, I wouldn't say familiar, but acquainted with. Also, it is interesting that in this expression, the spin density is dimensionless, right? So this factor in case of singlet just comes to a constant. And it cancels with 1/2 up front, and then we come back to regular LDA expression. So if our spin density is 0 everywhere. So in case we are going a little behind LDA, the corrections, it is just an example how correction may look. So this is the part that being integrated. So LDA term rho in power 1/3, and correction looks like algebraic expression of variable x, which is gradient of density in respect to density in power 4/3. And it includes like hyper exponential sign and powers, and it is one of the simplest functionals behind LDA. If you look on they're not secret, they're published in papers and textbooks, but they expand very quickly to take the whole page. And there are some derivations and theorems to justify these little corrections. Okay, and I think it's enough for today. So please ask any questions or bring up any subjects to discuss if you want to. David, everything is fine? No questions?
Yeah, I'm okay.
Okay, good. Kurt?
Yeah, I think I'm good for the moment. My brother's got supper ready here, so.
Okay, good. Then we are finishing. Queenie, do you have anything, any homework for me? I hope no. I'll check when we meet on. I hope there will be no snow on Tuesday, and I'll check if we need to go over this material again, or I probably can summarize it in like squeeze in like 3 slides and then go further, so that we complete the program within the semester. Okay. I will be very happy to answer any questions and contribute to your projects. So use me as a resource. And let me announce completion of this informal meeting and wish you pleasant weekend due to the snow. Okay, I'm going to close the connection if there are no objections.
Nope.
Okay, then have a nice weekend, and I'm departing. Kurt, no questions?
No questions. Just trying to figure out how to, like I said, doing this on my phone here. So,
Okay.
Yeah.
Okay, then I'm disconnecting with your permission.
Oh, yes, go ahead.
Okay.